This is Dr. Carroll. Today's video is about hashing and handling collisions. So as a review, let's insert the first several squared numbers into a hash table. Okay. So the first question is how big of a hash table should we have? Well, let's just go with a table size of 7. Okay. Now that and remember, it's important to have a hash table that's a prime number, and 7 is a prime number. The next question is what is the hash function then? Well, if there's no hash function given, a good one to assume is just using the modulo operator on the table size. That's going to distribute the entries into the hash table evenly through it. And if you get a number too big that's beyond the size of the hash table, that's fine. It'll bring it back into the range. So if you do modulo the table size, it'll always be a valid index into the hash table, and it'll spread the numbers out, assuming that the numbers are an even distribution. So let's see that example. So here we have our hash table. It's just an array, and we insert 0, and 0 mod 7 is 0, 1 mod 7 is 1, 4 mod 7 is 4. Now we're going to insert 9. 9 mod 7 is 2, because we subtract off the 7. And now let's insert 16. 16 mod 7 is 2, which is going to, what? Collide here with 9. So what do? We need some way to resolve the collisions, or to be able to handle them appropriately. So, and that brings us to two major schemes, separate chaining and open addressing. Okay, so let's start with separate chaining. Separate chaining is a common technique to resolve collisions. It allows the hash table to accommodate more than one item in the same location. Now, we could have each hash table location be an array. The arrays are called buckets. The downside is that it's not dynamic. We've just prolonged the problem, but the problem is that we're going to eventually run out of space. The other solution is to make it dynamic then, and we could have each location in the hash table be a linked list. So effectively, the size of the hash table then is dynamic, because as we have a collision into the same hash index, the list will just grow. Typically, you want to add on the beginning of the list just because that's fast, and we also benefit from the locality that we're likely to see that same entry again if we're looking for it. If the lists get really long, you can do some fancy structures like another hash, or a binary search tree, or something along those lines. Okay, and let's see an example here. Okay, so now that we've changed, the hash table doesn't contain entries anymore. It contains pointers to lists, or it contains lists, basically. So I've decided to draw the hash table a little bit different. So now when we insert 0, our hash function here reveals that it indexes 0th position, and we show that there's a linked list, this showing this being the null or ground symbol. And then we insert 1 in the list, it hashes to 1. Insert 4, we insert 9 just as before. Now we insert 16, and what we do is we push it to the front of the list and extend the list that way. Now if we insert 25, 25 mod 7 is going to hash to 4, that's fine. We're going to just push the other entry down into the linked list, and we can add 36 in, and that's going to push that entry down. And remember from the introductory video that the load factor alpha is the current number of hashed items divided by the table size. Well, in that last example, we had 7 items that we inserted, 0, 1, 4, 9, 16, 25, 36. And the size of the table is 7. So then we have 7 divided by 7. So the load factor for that example is going to be 1.0. And for separate chaining, the load factor is the average length of all the lists, including the lists that have a length of 0. And that's going to become important as we talk about efficiency in a different video. The other main approach to resolving collisions is open addressing. If you remember from the terminology, open addressing is where we're going to look for an open position, one that's available. We're going to talk about several different schemes of how to approach this. First, let's talk about linear probing. And it searches the hash table sequentially, starting from the original location and specifying by the hash function, and this is called the probe sequence, to look for an open position. Okay, and so we need to modify our hash function to include this probing sequence. We'll call it f of I. And so f of I is the probing sequence. Now f of I needs to have some qualities, like the first time we call it, we don't want it to change anything. It just needs to be the original hash function, basically making it moot point. In implementation, you'd only include it actually f of 1 and greater. Okay, and then for all other times, it's just we'll step that many times. We'll add that many more times our try. So we try it once, we'll add one. Next time we'll add 2. Let's see an example that'll help flush this out. Okay, here we're going to insert 0, and now notice I've modified the hash function here to include our f, and initially it's f of 0, so 0 plus 0 equals 0. And 1, it's 1 plus 0. 4, we don't need to use this until we have a collision. 9, so same as before. Now when we get to 16, we're going to try and insert 16. And so the original hash function here is 16. And then we're just adding 0. It maps to 2, but as we've noticed before, there's a collision. So then what we do is we try the next one, the next open one. And luckily we found a position, so we insert it there. Ah, darn it. 25 had a collision too, right here at 4. So we'll try the next one. Now, to get 36 in there, it initially indexes to the first position, but then we try that one the 0th time, didn't work. First time, second time, third time, fourth time. The 5th time, the 5th time adding in the probing sequence, then we finally find that position and are able to make that work. To search then, we're just going to apply that same hash function, including the f of I, and follow that same sequence of events so that we can get back at the original one that is stored in there. Now, let's take a look back at this sequence. What if we deleted, say, 9 here? What would happen then if we were to look for 36? Well, we'd apply the same hash function as we did before, h of 36 and f of 0 to start with, and would map to here, and we wouldn't find it. So then we'd look, and if 9 was deleted, it'd say that it was empty. Well, then we might be prone to think that, hey, it's empty, that means 36 was inserted after this. Well, so deletions become a slight issue here. And so what we need to do with deletions is we need to mark that the item at that index has once had an item that it is deleted. And this is in contrast to being empty. So we need to initialize each index as being empty, and then if an item is deleted, then we'll mark it as deleted. What we need to do now is update our search function. So we apply the hash function until we find either an empty cell or the key that we're looking for. Okay, and that's linear probing, and we'll talk about its efficiency in a different video. Okay, well, linear probing unfortunately suffers from primary clustering. That if we get a whole bunch next to each other, the probing sequence is just going to pile them up and up and up and up. And so that's one of the big drawbacks of linear probing, is that primary clustering happens. So to address that, we have quadratic probing. And so it searches the hash table beginning at the original location. But now instead of incrementing by 1, we're going to increment by the squares. So f of I is then I squared. Now remember, f of 0 had to be 0. That's fine. 0 squared is 0. Okay, so we're doing well, and we can do that. So let's see an example. All right, here's our example. We're just going to pick up. We've already inserted 0, 1, 4, 9, no collisions, and it's becomes interesting when we have a collision. So when we're trying to insert 16 here, hashing 16, so 16 mod 7 is going to give us 2, and then we don't need the probing sequence yet, and we need to take all of this into account and mod by the table size so we never go over it. We get 2, and so we get a collision. And so with quadratic probing, we're going to take 1 squared, and luckily we find a match for that, and we can insert it there. Okay, now let's look at 25. 25 initially maps to 4, that's a collision. So then we start a probing sequence, and luckily again, 1 squared takes us to the next position, and we're good. Now what about 36? Turns out, and I only calculated the first 1,000 steps for F, and none of them map to here. So there's some drawbacks when the table gets very full for using this. Now, there's another drawback too, and that's, now we got rid of linear probing because we could jump far away from that pile up and quickly, and the more steps we have to take, the further we're going to jump away. But the problem is, what if we map to that initial location, and then each one of those that collide at that same index are going to follow that same quadratic probing sequence, and then we have secondary clustering. Well, that's not very good. And so that brings us to double hash, which will address this issue. And what double hashing does is it uses 2 hash functions. It uses the original, the first one that specifies the location, and then the other one gives the step size. So a good hash function to use would be something like r minus r modulo r, where r is the prime number just smaller than the table size. You're getting the picture that use prime numbers all over the place, right? Good, good. And so to update then our hash function, f of I is going to be I times our second hash here. So when I is 0, then f of I is going to be 0 as required. And then as we go, we hash to a different location, which is great when we have 2 keys that collide, that they're different at the same location. Well, the secondary hash is going to send them on different probing sequences to where to look, but it's repeatable, so after we insert it, we can find it. Let's see an example. Again, we've already inserted 0, 1, 4, and 9, and then it gets interesting when we do 16. So we try to do 16. We have a collision, and then with f of 1 here, we're applying r minus x mod 7 here, and that's going to equal 4. So then we add 4 to our step counter, and so we get 6, and great, that spot was empty. Now let's insert 25. Again, 25 is going to, I'm sorry, that's an error. 25 is going to map to 4, and then we would, after we find that, we try to insert it, then we're going to add, we're going to try first f of 1, which is going to take 4 plus 5, which is going to map to here, where 9 map. Then we're going to try 2 times 5, so that's 5 more, and that's going to map to here, and then we try 5 more, and then eventually f of 3, the third step, we find it. Now if we wanted to search for 25, we'd apply the same criteria again. We'd look at the initial location, and then we'd start searching for the other locations until we either find an empty cell or we find the one that we're looking for. Okay. For 36, when we go to insert it, this one does map to 1. Copy and paste error, sorry. There's a collision there, and so 4 hops later, we try, this is each hop we're going to add 4 to. So 1, 2, 3, 4, nope, taken. 1, 2, 3, 4, no taken. 1, 2, 3, 4, no taken. 1, 2, 3, 4. Great, it's open. And we can deterministically find it again. Now, granted, this is a very small table size, and so there's some things going on here that you want to see in hash tables that are large as they should be. Okay. And that concludes the video about handling collisions in hash tables.